Hello, everybody. Welcome to lecture number 13 in MA 283 Linear Algebra. So in this is week 6, and this week we're going to start on chapter 3 of our lecture notes, which really follow on from chapter 2, where we were concerned about the key concepts of linear algebra, such as basis and dimension of a vector space. So in chapter 3, we're going to be really using the basis concept quite a lot. And we have a couple of main themes, which will kind of run through the whole chapter, even though we'll be looking at different elements. So first is that it's useful to be able to move between different bases for describing what's going on in a vector space. And this is particularly useful when you're talking about linear transformations. And as we know, linear transformations are functions that go between vector spaces. And it may well be that even if you're in a vector space which has a standard sort of natural basis, that one basis may be far better than another for describing the behavior, for example, geometrically, of a particular linear transformation. So the standard basis is not always the most useful one. And then the third theme, I suppose, is that everything, once you've got a basis in mind, can be interpreted in terms of matrix algebra. And although the setup and mechanisms for that take a little bit of work, the payoff basically is that you're working in a sort of concrete environment of matrix algebra where you can do calculations, where you can really figure out in a fairly direct way what is going on. So just to, on the second point there, I'd like to just share an example to sort of try to explain this point about how one basis may be better than another one for describing what's going on with a particular linear transformation. Okay, so here's an example. And we have a low-tech solution today. My tablet has failed. But we're talking about a linear transformation T, which goes from R3 to R3. And what it does is just rotate through 180 degrees about the z-axis. And we have a standard basis of R3, which consists of the elements E1, E2, E3, where E1, E2, E3 are the usual standard basis vectors. So E1 is the vector with entries 1, 0, 0. E2 is the vector with entries 0, 1, 0. And E3 has entries 0, 0, 1. And so our setup is like this. Here are the coordinate axes of R3. So as usual, we have an x and a y axis, which are often sort of envisaged as making a horizontal plane. And we have a z-axis, which is vertical, perpendicular to both the x and y axes. And our three standard basis vectors, just each are of length 1 and point in the positive direction along the x, y, and z axis, respectively. So E1 is like this, E2 is like this, and E3 is a vector of length 1, pointing up along the positive direction of the z axis. So that's the sort of geometric picture of the setup. And our linear transformation T, because it's just a rotation through 180 degrees about the z-axis, we can figure out what it does to each of E1, E2, and E3. So E1 gets rotated about the z-axis through 180 degrees. So basically the point here, which is at the end of this arrow, is 1, 0, 0. What happens to it after a 180 degree rotation about the z-axis is that it lands at minus 1, 0, 0. And the coordinates of minus 1, 0, 0 in terms of the basis E1, E2, E3 are, well, it's just minus E1. E2, similarly, E2 is 0, 1, 0. So here it is, and the point at the sort of end of the arrow there is 0, 1, 0. When we apply a rotation about the z-axis through 180 degrees to E2, again, it sort of lands over here on the negative side of the y-axis. So we get 0, minus 1, 0, and that is minus E2. And T of E3, well, E3 is actually sitting on the z-axis. So when we rotate about the z-axis, E3 doesn't move at all. So we can say easily what happens to the three elements of the standard basis of R3 under this particular linear transformation T. They just basically all get moved to a scalar multiple of themselves. And we can indeed write down the matrix of the transformation T with respect to the standard basis. So the matrix of T, in its first column, would have coordinates given by entries given by the coordinates of the image of the first basis vector E1 with respect to T, where the image of E1 is minus E1, so that has coordinate minus 1, 0, 0 with respect to E1, E2, E3. Second basis vector E2, its image under T is minus E2, so its coordinates with respect to E1, E2, E3 are 0, minus 1, 0. And the third basis vector E3 just gets fixed by T, so its coordinates of its image under T are just 0, 0, 1. So that's fine. And I guess the point here is the standard basis is very much the natural choice for describing this particular linear transformation T. The images of the three standard basis vectors all have very nice descriptions with respect to the standard basis. And we have a kind of a physical picture maybe of what this linear transformation does. It just takes everything and rotates it through 180 degrees about the z-axis. So it's geometrically, it's a relatively sort of straightforward linear transformation. The point that I wanted to make, though, in respect of this was, suppose you had some linear transformation that did something very similar, but instead of rotating everything about the z-axis, it took some axis passing through the origin, which is labeled here in red. So just imagine this red line as, as making an angle with all three coordinate axes pointing off in some different direction, so it's not parallel to any of the coordinate axes. And if we have a linear transformation T that does a rotation through 180 degrees, let's say, around this axis, let's call it S, then if you were to write the coordinates of the images of the standard basis vectors with respect to that linear transformation, they wouldn't really be recognizable in any way. There'd just be some vectors in R3, and you wouldn't be able to read from their coordinates that what this transformation does is actually a rotation through 180 degrees about some axis. So the comment, which is just kind of really the point of this example, and we're not going to answer the question right now, but suppose we had another transformation. Let's call it T dash. Is another linear transformation. From R3 to R3. And suppose that what T dash does is rotates everything about some other axis called S, written there in red in the picture. Okay, so if we try to describe the behavior of T dash in terms of what it does to the standard basis vectors, the standard basis is not really the best one for describing this transformation T dash. And what I mean by that is if we were to write down the images of the standard basis vectors E1, E2, E3, which are labeled there in the picture in black, they point along the coordinate axes. And if you were to describe what the rotation around S does to each of them, the images wouldn't be anything sort of recognizable in terms of E1, E2, E3 that would reveal that what S actually does is just a 180 degree rotation about some axis. So what would be better to choose for describing S would be an axis consisting or a basis consisting of a vector pointing along parallel to X and maybe then two other vectors that are perpendicular to S. So a basis consisting of a vector parallel to S and two more that are orthogonal to that and to each other maybe. And two more vectors orthogonal to that and to each other. Would be the preferable thing for such a description. So with respect to such a basis suitably chosen, maybe we'd get a matrix for T dash that would resemble that nice diagonal matrix for T that we have here. This matrix is diagonal, which is really sort of the best you can hope for in terms of a matrix that's easy to manage and easy to deal with. So the matrix of the transformation T dash about this axis S with respect to the standard basis wouldn't be diagonal because the image of the vector E1 under that rotation about the axis S wouldn't just be a scalar multiple of E1. But if we were to choose a vector perpendicular to parallel to the direction of S, or maybe perpendicular to it, the image of that under the transformation T dash might be a scalar multiple of itself. So we might get a basis with respect to which the matrix had a nice description. So that's kind of the point of this comment on the first slide today, that the standard basis may not be the best for describing every linear transformation that one might want to look at. Okay, so back to our slides then. So another thing that I just wanted to mention, because, okay, hopefully that example might be helpful in making the case that we might want to be able to move between different bases of R3, for example, to describe different linear transformations. So one question that we might ask would be, okay, well, suppose a basis for R3 should consist of three vectors, each with three entries. So if we have 3 vectors in R3 or 5 vectors in R5 in our hands, how do we know whether they form a basis or not? So how to recognize a basis of R3, or of Rn in general, or of the vector space Fn, consisting of all column vectors with n entries over some field F. So the dimension of the space Fn for any field F, for example, the real numbers, is n, and the standard basis of Fn consists of the column vectors e1 through en. This is a fairly standard notation, where e1, for example, has a 1 in position 1 and zeros in all other positions. E2 has a 1 in position 2, 0 everywhere else, and so on. And so it's pretty straightforward to see, I think, that these particular column vectors span the space of all column vectors over the field F. So in R3, for example, here's our standard basis again, and certainly any column vector ABC is just AE1 plus BE2 plus CE3. So it's a linear combination of E1, E2, E3. And equally well, we can recognize that E1, E2, E3 are linearly independent from the fact that each of them has exactly one position where it has a non-zero entry, and that position doesn't have a non-zero entry in any of the other EIs. So for example, if you have a linear combination of these 3 vectors that's equal to the 0 vector, the coefficient of E1 must be 0 because the entry in the first position is 0. The coefficient of E2 must be 0 because the entry in the second position is 0, and so on. So this basis is kind of particularly conducive to observing that it's a spanning set for Rn and that it's linearly independent. Okay, so that's fair enough. And I suppose one thing that standard basis does for us is it convinces us that the dimension of Rn is indeed equal to n. There's one basis with n elements. That means that any basis should have n elements. So, okay, how should we recognize whether some collection of vectors is a basis for Fn or not? Well, first requirement is it should have n elements. Each of them should be a column with n entries. So some sets of 3 column vectors in R3 are bases of R3 and some aren't. And how are we supposed to know? So an answer to that question in terms of matrix algebra is given by this theorem. So I'd say, my advice in how to deal with this theorem, how to think about it, how to read it, how to consider what it's saying, is to first of all try it out with a few examples for R2 or for R3, nothing bigger than that, and sort of satisfy yourself that it works. And then if you want to kind of come back and have a look at the proof, it's basically sort of translating the statement into matrix algebra. So supposing that we have a set of vectors in Fn, so in Rn, so like think of a set of 3 column vectors in R3. Then the assertion is that this is a basis for Fn in general, or Rn in particular, if and only if, when you write down the matrix, the n by n matrix, whose columns are these n vectors, that it's invertible, that it has an inverse in the space of n by n matrices. Okay, and to see why that is true, so the picture here is, your matrix A is a matrix whose columns are the vectors in your potential hypothetical basis. If A has an inverse, then A inverse is equal to the identity, and the first column of the identity matrix is 1, 0, 0, 0, the first standard basis vector. So if the product A by A inverse is equal to the identity matrix, that means that the first column of the identity matrix is the linear combination of the columns of A, whose coefficients are the entries of the first column of the inverse of A. And that's saying exactly that the first standard basis vector is a linear combination of the columns of A. Similarly, by looking at the second column of the identity here, we're saying that the second standard basis vector, which is the second column of the identity matrix, is the linear combination of the columns of A, whose coefficients are the entries of column 2 of the inverse of A. So we're just using the fact that, when you multiply a matrix on the right by something, basically the columns of the product are linear combinations of the columns of A itself. So this is this product A by A inverse equal to the identity matrix is essentially saying that every column of the identity matrix is a linear combination of the columns of A, which is exactly saying that all the entries, all the vectors in the standard basis are linear combinations of the columns of A, which is saying that each of those is in the linear span of the columns of A, which is saying that the columns of A form a spanning set for all column vectors of length with n entries, because all the standard basis vectors are there, so all their linear combinations are there as well. So that's one way to see how it follows from the fact that A has an inverse that its columns form a spanning set for n-dimensional space over whatever field you're working with. Okay, on the other hand, if the columns of A do form a basis for Fn, sorry, there's a typo there, the n should be a superscript. Then in particular, E1 is a linear combination of the columns of A. So E1 is A multiplied on the right by some vector whose entries are the coordinates of E1 as a linear combination of the columns of A. And doing the same thing for each of the other EIs, each of the other standard basis vectors, what we discover are the columns of the inverse of A. So the statement that A has an inverse is exactly equivalent to the statement that its columns form a basis of Fn. So I'd say with this theorem, don't worry so much about proving it. I won't ask you to reproduce the proof of this one. It's kind of interesting, I think, to figure out for yourself and to follow the steps of the proof to satisfy yourself about how this can be understood in terms of matrix algebra. But the statement of it is really what I kind of would like you to keep in mind and to have as a kind of working piece of knowledge, that a set of column vectors with n entries is a basis for Fn if and only if, when you make a matrix with those columns as the columns, that matrix to be invertible. Okay, so that's, I suppose, a sort of, we'll be using this throughout this section. It's a note about how to recognize a basis of Fn, the space of column vectors. Okay, and then the real theme that is going to occupy us quite a bit throughout this chapter is when you've got more than one basis in mind, how to move between them. So how to move between the coordinates of a vector written with respect to one basis to the coordinates written with respect to another. And really the key to this is the content of the last slide, but we'll have a look with an example and we'll figure it out as we go. So supposing that we have another basis of R3 besides the standard basis. And let's just suppose that the basis that we have in mind is this one, with entries B1, B2, B3, elements B1, B2, B3 in that order, let's say. So that so B1, B2, B3 obviously are three columns in R3. You can easily confirm using the property noted in the last slide that these three vectors do indeed form a basis of R3, because when you write them as the columns of a matrix, that matrix is invertible. It has non-zero determinant, or it has an inverse that we can write down. Okay, question. Suppose we have some vector in R3 in mind. For example, the vector 2, 1, 3. And here I mean the vector whose the element of R3, which is the column 2, 1, 3. So 2, 1, 3 are its coordinates with respect to the standard basis. Question. What are the coordinates of V with respect to this basis B, consisting of these three elements, B1, B2, B3? Okay, so in other words, if we want to write this vector V as a linear combination of B1, B2, B3, what should the coefficients be? Those coefficients are the coordinates of this vector with respect to that basis. Okay, another question is, and a very reasonable one, is why would we want to know this? You know, we have V, we know what it is, it's written perfectly reasonably as it is. The answer, I guess, hopefully might be partly given by that example with the rotation about some axis that isn't parallel to the coordinate axes, that there might be we might have a reason for wanting to describe a vector with respect to that basis instead of with respect to the standard basis. For example, if we're trying to describe some linear transformation with respect to which these three vectors have some kind of nice or special properties, like being an axis about which a rotation is taking place or something like that. Okay, so we're going to come back again and again to why we would want to know this, but that's one reason. So question for now is just a technical one. If we want to do it, how do we do it? Okay, so what we have is V written in terms of the standard basis vectors. So V is 2, 1, 3. It's 2E1 plus 1E2 plus 3E3. So we know how to write V in terms of E1, E2, E3. So the assertion is, if we knew how to write E1, E2, E3 in terms of B1, B2, B3, then we could use that to write V or any other vector in terms of B1, B2, B3 if we already had it written in terms of the standard basis. Okay, so let's figure out first then, how do we write the standard basis vectors as linear combinations of the elements of B? And we've already actually answered this in the slide where we had the discussion of invertible matrices, but let's have a look at it for this example. So the B coordinates of E1 are the values x, y, z, for which x B1 plus y B2 plus z B3 is equal to E1. And that is exactly what is written in this matrix equation. On the left-hand side of it here, we have the matrix vector product of B, whose columns are the basis elements of the basis B, multiplied by the vector x, y, z. So that is just the linear combination x B1 plus y B2 plus z B3. We want to know when that's equal to 1, 0, 0. Well, that happens if we just take this as a matrix equation and multiply it across by the inverse of B. The values of x, y, z, which do that job for us, are what we get if we multiply 1, 0, 0 in front by the inverse of B. B being the matrix whose columns are the basis vectors in the basis B. Okay, so this means that the values x, y, z, the coordinates of the standard basis vector E1 with respect to the basis B consisting of B1, B2, B3 is just the first column of the inverse of B, which is exactly the inverse of B multiplied by the column 1, 0, 0. That's 1 times the first column plus 0 times the other two columns. So the coordinates of E1 with respect to the basis B are just the entries of the first column of the inverse of B. And in the same way, the coordinates of E2, oops, typo there, of E2 and E3 are given by columns 2 and 3 of the inverse of B. So if we write down the inverse of B, then we have the coordinates with respect to the basis B of the standard basis vectors E1, E2, E3. So here's the inverse of B. So you can figure out the inverse of B by whatever your preferred method is. Either work out the 2 by 2 determinants, the cofactors of B, or start by writing B, by writing the augmented matrix, which has B in the first three columns, identity matrix in the second three, and reducing that to reduced row echelon form. And what will be written in the last three columns at the end of that is the inverse of B. So looking at, for example, at column 2 of the inverse of B, we can confirm that its entries are the coordinates of E2 with respect to B. Okay, so just to confirm that the coordinates with respect to the basis B, consisting of the three basis vectors B1, B2, B3, which are the columns of the matrix B there, we're saying that E2 should be equal to the second standard basis vector E2, which has entries 0, 1, 0. That should be equal to the linear combination of the columns of B obtained by taking the coefficients there in the second column of the inverse of B. So 1 times 1, 1, minus 1, plus 1 half times minus 1, minus 1, 2, minus 1 half times 1, minus 1, 0. And we should hopefully be able to confirm that if we've got the calculation right of the inverse. So this would be in the first entry. We have 1 minus 1 half minus 1 half, which is 0, as we would hope. Second entry, we've got 1 minus 1 half plus 1 half, which is 0, which is 1, sorry. And at the third entry, we have minus 1 plus 1 half times 2 minus 1 half times 0. So we end up with 0, 1, 0, which is indeed equal to E2. So this is, this is not saying anything. We already knew from the fact that these two matrices are inverses of each other, that when we multiply B on the right by the second column of its own inverse, we should expect to get the second column of the identity matrix, which is indeed the matrix E2. So there's nothing much going on here except just to confirm the assertion that the coordinates of the standard basis vectors with respect to B are indeed given by the columns of the inverse of B. Okay, but the question that we started with was how to write the coordinates of some random vector in R3, for example, this V, with respect to the basis B. Okay, so what we'll do in general, this is a kind of bit of fussing that is always needed when we're moving around between different bases. We'll just write, if we want to refer to the coordinates of some vector with respect to the basis B, as opposed to the standard basis, and write them into a column, we'll just write a subscript of B on that column to indicate that we're talking about the B coordinates and not the standard coordinates. So basically, the problem now that we know how to write E1, E2, and E3 in terms of the basis B, the way that to use that knowledge to write V in terms of the basis B, we will now figure out. So we know that V is 2 times E1 plus 1 times E2 plus 3 times E3. That's how it's written in terms of the standard basis. And that tells us that the B coordinates of V should be 2 times the B coordinates of E1 plus 1 times the B coordinates of E2 plus 3 times the B coordinates of E3. Okay, and another way to say that, of course, is that each of these B coordinate vectors is a column with 3 entries. So this is saying we should take the column that writes E1 in terms of B multiplied by the scalar 2, plus the column that writes E2 in terms of B multiplied by the scalar 1, plus the column that writes E3 in terms of B multiplied by the scalar 3. And of course, we have another way to do that. That's just the matrix vector product, which we get by taking the 3 by 3 matrix with these 3 columns and multiplying it on the right by the vector whose entries are the scalars 2, 1, 3. So it's just this matrix vector product. But of course, this matrix is nothing but the inverse of the matrix B that we started with, whose columns were the basis vectors B1, B2, B3. So this matrix is nothing but the B inverse that we've been working with. So what we're saying is, if we want to write the B coordinates of a vector V, all we need to do, or what we need to do, not all we need to do, we've done a fair bit of work to get to this point, but at this stage it is relatively straightforward. We could just take the vector v written with respect to the standard basis and multiply it on the left by the inverse of the matrix whose columns were b1, b2, b3, the basis vectors of the basis b that we want to move to. And when we do it in this particular example, we get 6, 9 over 2, 1/2, and you can confirm straightforwardly for yourself that if we do take the vectors b1, b2, b3 of the basis b that we started with in this example, and take that linear combination of them, that we do indeed get nothing but the vector v with entries 2, 1, 3. So a little bit of lingo just to finish this off, which will be useful for us to recall. So to find the b coordinates of any vector in R3, that example v being the typical one, what we need to do is multiply the vector v as it's given to us in its standard coordinates on the left by the so-called change of basis matrix from the standard basis to b. And what that change of basis matrix is it's the inverse of the matrix whose columns are the elements of the basis b. Okay, so we have this concept of the change of basis matrix from moving from one basis to another. And basically the way it works is if we have a vector written with respect to a particular basis, let's say the standard one, and we want to write it with respect to a different basis, let's say it's called b, then we have a change of basis matrix from the standard basis to the basis b. The way it works is it's the inverse of the matrix whose columns are the entries of are the elements of the new basis b, and we just multiply our original vector on the left by this change of basis matrix, and the result of that is the coordinates of the vector with respect to the new basis. So we'll use this quite a lot, and we sort of incorporate it into our general arguments, so it'll be helpful for us to be familiar with it. So that is the first section of chapter 3, and I suppose the key points in this section are, first of all, how to recognize when a set of n column vectors in Rn, or generally over a field Fn, forms a basis for that space, and the answer to that is when they form an invertible matrix, when you write them as columns of a matrix. The second thing is to recognize that elements of our vector spaces, Rn or Fn, have different coordinates with respect to different bases. And thirdly, then to kind of be aware that we have this method of using a change of basis matrix to write the coordinates of any vector with respect to a given basis. And as we get into the study of linear transformations a bit more, we'll see what we mean by one basis being preferable to another for inspecting or observing or thinking about certain phenomena. Okay, that's it for today. Thank you very much, everybody, and see you next time.